All right, well, the next kind of reaction is also a double replacement reaction, and this is an acid-base reaction, so always also double replacement. Now, there is no looking at solubility rules for acid-base reactions. Turns out if you have an acid and a base and you bring them together, there's always a reaction. So you don't have there's nothing to look up, okay? Now, the thing you have to be careful of is that strong acids and bases completely ionize, and so in a net ionic equation situation, you'll split them up completely, okay? Now, oftentimes when we do acid-base reactions, and 90% of the time in this class, right, you have something with hydroxide, and you have something with hydrogen ion, and the other part that you're always going to be making is H2O and then something else. And that something else would be with the sodium and the sulfate. So it's actually like a little faster to do like acid-base reactions because it's half of the product is generally already predicted for you. It's usually water. Okay, so let me show you how this works out. I'll do it sort of the way we learned it, and then I'll sort of break it down for you, sort of the way you can kind of get a little bit of a shortcut when you do it. Okay, so the way we did it before is I would write Na plus plus, let's say OH minus. I split it into its ions, right? So I have H plus and SO4 2 minus. Now this is not balanced. And it turns out it doesn't really have to be balanced at this point. And one of my products is going to be these guys going together. The HOH, that gives me my H2O, and the other product is going to be this. So what you can do is you can just write Na2SO4. And that'll be, right, the molecular equation. It's not balanced yet. So what I'll have to do is add a coefficient. And here's the thing to think about, right? For every H, you're going to have another H2O because, right, the H goes with an OH to make an H2O. So in the balancing, this subscript that's here, or sometimes the subscript that's here on the OH, tells you how it's going to balance ahead of time. So this is going to be a 2 here, and it's going to be 2 here like that. Now, that's the molecular equation. This is aqueous. Acids are aqueous. Even there's not a solubility rule for acids. They're just aqueous. They're always dissolved. Okay. Maybe I didn't write that. Let me write this little note up here. Acids are aqueous. It's not true for all acids, but in this class it's true. Acids are aqueous, like that. So they're aqueous. Water is a liquid, right? You knew that. And then sodium sulfate, this is aqueous. And it's because it's group 1. And you'll see that a lot because a lot of times the bases are sodium hydroxide, potassium hydroxides. They're the soluble hydroxides, which are usually group 1s. So now to write the total ionic equation, I just split everything up. I've got it balanced, so I'd say 2 Na plus 2OH minus, I'll use a squiggly line like that, plus 2, well, I'll tell you the real way to do this one. It just drives me crazy if I don't do it right. It's supposed to be like this. H plus HSO4 minus. Now, if you write 2H plus and SO4 2 minus, that's okay. But it turns out the first hydrogen's strong and the second one's weak, and that's not a detail. Like, we won't get to that until late into the semester, which is like 3 weeks, 2 weeks from now, but still. And then I'm going to have my reaction arrow, and then it'll be the products, which will be H2O as a liquid, and Na2SO4. So Na plus SO4 2 minus, because those are aqueous like that. So that's the molecular is up here. The total or complete ionic equation, and then the net, I would get rid of my spectators, and this might get a little tricky, but I can't get rid of the OH. Where'd my the OH ends up over here, right? And And my H actually ends up over here. And my HSO4 ends up over here. And the only thing that is really a spectator the way this is written is this guy and this guy. So my net ionic equation would be 2OH minus plus H plus HSO4 minus makes H2O liquid. Oh, and that has a 2 in front of it. Sorry, I left that out earlier. I just didn't copy it down correctly. Plus SO4 2 minus. And then all these ions have squiggly lines on it for being soluble. Okay. Now we're going to do HF and KOH. Right. Now this is a weak acid. And again, the reason it's a weak acid, if you go back to the list of acids that I gave you to look at, it's not on that list. Okay. And KOH is group 1, so you know that that's soluble, right? So actually, I wanted to show you how you do this without writing everything out. So remember, one of the products is going to be water. So the other part of it is going to have the F and the K. Because the H and the OH, right, they're going to give me water over here, like this. So I just take the other part and make a compound out of it. So I know potassium is positive and fluoride is minus, like that. So it's just going to be KF, like that. Now water will still be a liquid. KOH would be aqueous, and HF would also be aqueous because it's an acid. Okay, so KOH is aqueous, HF is aqueous, H2O is a liquid, and KF would also be aqueous like this. So now what I do is, this is my molecular equation. I'll split it up into its ions, and so I'll have the following, and this is the trick part. HF, another trick, weak acid, you leave it together, it's still aqueous like this, okay? Now normally I put a squiggly line, but I do want to emphasize that that stays aqueous. Plus K plus OH minus makes H2O liquid plus K plus F minus, and these are aqueous like that. So the only spectator I have, I'll circle that in bright pink, is potassium ion like this, and everything else is the net ionic equation. Okay.